Well, good morning, everyone. Or maybe I shouldn't say good morning, good afternoon, or good night, wherever you are. Welcome to lecture 2. Our topic for today is kinematics of particles. In the chart that I showed you, this is the very first topic. We start with particles. As I said, we assume the size is so small that we can consider all the mass at its center of gravity. We have different topics related to particles. We started with kinematics. When we talk about kinematics, we just talk about velocity and acceleration, but we are not going to talk about forces, how these acceleration comes from. That's the next topic. All right. So before I start, do you have any question or concern? Are we good? All right. So let's then start with the first topic, which is rectilinear motion. So when we say rectilinear motion, it means everything moves on a straight line. And this line can be any line. It can be a vertical line, a horizontal line, or any line. So let's say I have a particles on this line, right? This particle. And let's assume this particle has a velocity, and velocity always is tangent to the path, right? So then we call this one our path, which is a straight line. And we have a particle moving along this path. So velocity, usually we show it by V, stand for velocity. And always when we talk about like kinematics, we should have a reference. Let's say this particle maybe started somewhere before it, but we are interested to study it from this point and for the rest of the motion. All right, so then what I will do, I say this is my, let's say, reference at the very point. All right, so this is then my reference when this particle started, or maybe at this point that I'm interested to study it. And position, usually we show it by S. Some people show it by P, but S, that's a letter we use in this course. And this particle may have an acceleration or deceleration. Acceleration when the speed keep increasing, and deceleration when, let's say, when we brake and the things that has a velocity is gonna stop, right? So velocity then, let's say for velocity, it can be again along for acceleration, it can be along the velocity, so which we call it an acceleration because it results in a speed being increasing. Usually we show it by A, but let's right now write acceleration, or it might be the opposite of the velocity. So like this direction, and this is when we brake, right? And we call it deceleration. So deceleration, all right? So all of this line has to be, of course, along this path, but because I don't want the picture to get messy, I draw them separately, right? So this is the picture that we have. Now let's formulate them. So position, as I said, in kinematics, we are concerned about position, velocity, and acceleration. We write acceleration, but as I said, it can be deceleration. But it's common just to call it acceleration. So position, it can be a function of time, right? So we show it by st. Because as the time passes, this s, this distance is changing. And then velocity, as I said, we show it by v. It can be constant, but in general, it can be a function of time. It means by time it changes. And the definition for velocity, you learn it in physics, is simply derivative of s with respect to time, right? If we take the derivative of s with respect to time, we get velocity. For simplicity, we just show it by s dot, all right? And then acceleration, you learn it, we show it by in physics with at, and the definition for acceleration is the rate of change in velocity, right? So then if it is the rate of change in velocity, simply it is dv divided by dt, which for simplicity or laziness, we can just show it by s double dot, all right? So these simple three formulas, let's call them 1 and 2, and this one 3, are the basic formulas for kinematics of rectilinear motion. We may combine formula 2 and 3 to make another formula, which can be useful. So let's combine 2 and 3 and see what we will get. If I combine 2 and 3, so what I will get, let's say for this formula, I know dt, like the formula number 2, dt is equal to ds over v, right? I just don't write the vt for simplicity, but you know. And, oh, this has to be dt. So, and the formula number 3, I just write it down as dt equal dv divided by a, right? So all I did, simply as you can see in this relation, I change the position of dt and v. Now, if I combine these two, because dt is equal to dt, I can write down ds divided by dv is equal to dv divided by a. So, and this one simply gives me what? It gives me, oh, I might have made a mistake somewhere. This is v, right? So then I will get v dv is equal to a ds. All right, and this is a very useful relation between velocity and acceleration and position. Something is unique about this relation. You can say what it is. Look at the parameters that we have so far. We have time, we have s, which is position, we have velocity, and we have acceleration, right? What is it about this formula? So if you notice, this formula doesn't have time, right? It is independent of time. So keep in mind, if you deal with a problem that doesn't talk about time, for example, how long does it take to get to this velocity or to get to this position, this formula can be handy. If you just have velocity and acceleration, then you can use this formula. So I'm going to write down here then for you, independent of time, right? And you can integral, of course, always. If I integral the first part, I will get v dv. And if I integral the second part, I will get a ds. So I say I have started from velocity v0. Maybe it is 0, but for a general formula, we say we started from velocity 0 and we get to velocity 1. And we started from position 0 and we get to the position 1, right? So any question, guys, so far? And don't be intimidated by, again, this math formula. It is just a start. You will see simply when we solve problems, even this formula becomes second nature. We just use them. Any questions so far, guys? So you learn what happened, right? 1 is position, s, 2 is velocity, which is derivative of position with time, and 3 is acceleration. We combine 2 and 3. In other words, what we did in 2 and 3, we get rid of dt, right? If you notice, we get rid of this dt, and what happens is we get to this nice formula, which can help us later to solve some problems. So let's call also this formula number 4. So later then when we use it, we know which formula we are talking about. Okay. So let's consider a very special case. Let's say a special case when acceleration is constant. So A is constant. Again, a review from your physics. We go back from this formula that we have, right? So we have position, which is s, that's good. Then we have velocity, which is ds over dt, right? And from here, if I write down ds is equal to v dt, all right? I have a formula here. And then let's go back. For A, AT is equal dv over dt. A is equal dv over dt. And from here, I can write down dv is equal to a dt. And if I integral this one, right, and I say we started from v0 and we get to v1, acceleration is constant, right? So then simply I can write down v1 minus v0 is equal to at. And if simplify it, v velocity is equal to at plus v0. Here I write v1, but it can be any velocity at any point, right? Because this particle, let's say at time t gets to this new point, which we call it v1. All right, or position 1. So now that I have the velocity, at equal to v0, at plus v0, and again, maybe let's remove this. For some reason, my pen doesn't work properly today. So let's get rid of this v1. So in general, we say any velocity after this point 0. So if I substitute this v in the previous formula, like here, then I will write the integral of ds is equal to integral of, instead of v, I replace it by at plus v0 dt. And again, ds, maybe we started from reference 0, we get to the point s, right? So, and acceleration is constant, time we start from time 0, and we get to the time t, any time. And if I simplify this formula, I will get s is equal to half of at0, t squared, v0 t, and maybe plus s0 if, again, we haven't started from position 0. So again, this formula, simple formula, you've seen it before in physics, can be handy sometimes, right? So we have then a relation between position and acceleration. We have a position between velocity and acceleration, and that's because a is constant. We cannot generally use this formula if a is not constant. Another special case, if there is no acceleration, if a is 0. So immediately you get that v is equal to v0, right? From this formula that we have, if you substitute a to 0, you get v is equal to v0. And we know when there is no acceleration, of course, velocity is constant. It's always equal to its initial velocity. And what about position? Well, simply s position is going to be v0 t, right? So nothing special, I guess, about this formula, but please stop me at any point if you have a question. The first few topics are super simple and review from your physics. Bear with me if they are repetition of things that you know, but it's better to build up these things together and nicely, and then we go from there, all right? So here, let me write down constant velocity, right? And then constant velocity. So if there is no question, I assume you're good. Let's then move on and let's solve one simple problem together. Okay, I'm going to give you a minute so you can read the question. I'll do the same and then we'll solve it together. I have a habit when I read a problem that doesn't have any, let's say, figure, I try to draw a figure for myself to simplify things. So apparently we have an airplane which is landing. So this is then the runway, right? So the runway for the airplane. And based on this question, because it doesn't talk about the size of the airplane, then we can assume it is a particle. So this is the airplane. And then this airplane, it says, a touchdown on a runway at 60 miles per hour. So then it's the speed here, V60, M stands for mile here, mile, P always per, right? Mile per hour. And then it says it decelerates, right? It brakes, of course, because it wants to stop. So when we talk about deceleration, always remember it is the acceleration is with a negative sign. So it says it decelerates to a stop with the deceleration rate of 10 feet per second squared. So then I know my acceleration. Let me write it down here. So my acceleration is minus 10 feet per second. We'd better write second, but for simplicity, I just write s squared. Okay, so this is all the information that we have. So the question asks, how long does it take? Oh, no, the first part, it says, find the required length of the runway, right? In other words, this plane is gonna come down and stop somewhere. We wanna know the length of this runway. Maybe after this end of this runway, there is maybe ocean. We don't want the airplane to go to the ocean, right? So it's critical then to know the length. Let's see what we have here. It's a constant acceleration problem. So good, we don't need to do any integral or anything. And the question, the first part of question didn't talk about time, right? It just asks us the required length without asking how long does it take. And always remember, when you have velocity, when you have acceleration, and you need to know the position, these three, position, acceleration, and velocity, without time, then your best formula is the one that we just found. Let's go up here. V dv ads. But let's also complete it for a constant case, because we didn't. Let me come back here. V dv is equal to a, or to do a better job, let me move all of these, because this is all for category of A0 down here. So V dv is equal to A ds. This is this formula, right, guys? Formula number 4, VdV equal AdS, which I'm going to solve it for this special case. So if I integral this formula again, and I say we started from V0 and we get to a velocity V or V1, then let's call it V1 because now we are integraling here for a constant, and A is a constant. Then what do I have? First part integral V1 V0 squared, and then we have also a half, right? It's equal to A, and let's say we start from S0 and we get to S1, a special case. So here S1 minus S0. If I simplify this formula, I will get V1 squared minus V0 squared is equal to 2A delta S. So this formula, in fact, tells me if I have the initial velocity, if I have the second velocity, and if I have the acceleration, I can figure out the distance that this particle or whatever has traveled. So I can find out delta S, right? Let's use this formula for this problem, see if it can help us. So let me write it down again. This is the formula we have. V1 squared V0 squared is equal to 2A delta S, right? Let's substitute the number that we have. So what is our V1? So this is V0 when we started, and this is our V1. We want these things to stop, right? So it is 0 then. Minus V0. So unit, it is mile per second, but acceleration it is in foot and second. So always the units has to be consistent. Let's decide and change everything to feet and second. Usually we convert the units to the smaller one. So then we don't touch these 10, this acceleration, because it is already in feet and second, but we need to change this 60 mile per hour. So we need to know how many feet are in 1 mile. Somebody remembers? I'm going to convert then these to 60. Let me write it down here. So we have 60 mile per hour, right? Or if I want to write it mathematically, 60 mile per hour. So we know that in each mile there is 5,280 feet, and every hours we know it is 3,600 seconds. So this is our velocity then. So I just write it down here. So then I can do the calculation all together. And this is that all squared. 2, acceleration is minus 10. Don't forget the sign. And we are interested in knowing delta S, which if we do the calculation, we can find delta S, but please check my calculation later. Maybe I made a mistake. So this is basically delta S from the point that we start and end. All right? Any question, guys, so far? Are we good? So maybe this is too simple for you guys, which I can guess because this is basically something that you've seen in your physics. So the second part of question is very simple. It asks how long does it take for this airplane to land or to stop? So since the acceleration is constant, then simply we have the formula V is equal to AT plus V0, right? And we want it to stop. So V is 0, acceleration is minus 10, we are interested in finding out time, and we have the V0, which is this number. If you notice, I haven't calculated V when I convert it. I try to carry all these numbers and put them in my calculators so I get a more accurate result. Especially for something like time, which is like the small digit also matters. 8.8 seconds, right? So I'll let you guys to quickly, if you want to take any note or if you have a question, ask me before we move on. I realize I need to get up a little bit earlier, not right before your class. Because in the past, I had to get up at least 1 hour earlier before the class to be ready to walk to the class. But now it's just I can jump from my bed and then come to your class. So then I realize the brain, like a Windows, needs to boot up. It takes some time to sort of adjust. So I'm sure some of you just get up from bed and maybe you are still in your bed and just turn on your laptop. Unless you are in other places, which it is your bedtime, maybe. You need to go to bed after this. So are we good, guys, so far? Good? All right. I'm just going to quickly check the chat. Maybe if there is a question, maybe if there is a shy person asking question in the chat. Oh, Rocky, sorry, you said, can I see the last slide? Sure. And walking, yes, I know. Oh, good number here, 5280. Eric, it's not 5,120. So you need to get up also early, like me. So, okay, I'll check the rest later. So Rocky, here is the last slide. This is the slide you asked. You guys better unmute yourself when you have a question like this and quickly ask me, because if it is in the chat, maybe 5 minutes later, I will find out. Are we good? Okay. Okay. So let's move on and solve another example. I'm going to again give you a few, not few, 1 minute to think about it, try to understand the problem. I'll do the same. And then we solve it together, step by step. So what it says, well, apparently we have some steel balls. Maybe they are like small bearings, like the ball bearings. And then we have this maybe mechanism or a slot in which they come right after each other and they fall down, right? Maybe this is part of a machine who makes, let's say, ball bearings, right? And what it says they fall down with the rate of 2 per second. So this is the rate, steady rate, 2 per second, right? We need to translate this. This is the key parameters here in this question. So if it says every second there are 2 balls, it means the time between each ball is 0.5 seconds, right? So then I would write it down, like sort of I translate that for myself in each 0.5 second, 1 ball falls, right? And then the question says, well, find out h, this is h here, the distance between two ball, any two ball, if 3 seconds has passed when the first ball drops. Like, let's say, if this is our reference, right? And this is the first ball, come down here. We don't know how much it comes. Let's call it H1. This is ball 1. Let's call this one 2. Okay. And half a second later, the second ball drops. So let's then call this distance H2, right? And
sorry, the question asked for 3 meters.
Oh, maybe a typo here. 2 consecutive balls when the low one has dropped 3 meters. No. The question asks what is h when this h1 is 3 meters? You're right. So this is h1, 3 meters. Right? Is it clear? Sorry, this is the ring in my phone. It's going to stop. So the question asks, find h, all right, this h, when the first ball drops 3 meters. Okay, this is the question. And this is all the information that we have. And also it says neglect air resistance. So now that we know what is the question, let's figure out how to solve it. I'm just going to give you 30 seconds to think about it. This is all the information that we have. So a good part of successfully solving a problem is to understand the problem, right? And the best things in this course, and maybe any other courses, is to draw a nice, clean diagram for yourself. When we get to the next part of the course, which we talk about rigid bodies, diagrams becomes very important. So, as I said here, H2, we don't know how much it is. H1, we know it is 3 meters, and we want to find out H. So what else we know about this problem? Is it a constant acceleration? It is, what information do we have? Any idea?
Is the acceleration 9.81?
Exactly, so that's a very good information. So we know this one is a constant acceleration, and it is just gravity, which we know how much is gravity. What else do we know about this? What is our initial velocity?
0.
0. Why? Because it falls, right? Whenever a problem says something is falling, so immediately you say at the reference, my V0 is 0. So we should be good to go then, right? Because it's a constant acceleration formula. We know, like we just learned, that this formula x half of a2 plus v0t, right? We have the reference and everything. So this is our main, basically, formula. We show it by x, but of course, x can be replaced by anything. So what then I will write is h1 is equal to half of acceleration is g and t squared, and I don't have velocity. So 3 meters, half of 9.81 t squared. From here, I will find out how long does it take for this ball to come down to this point. So it takes 0.78 seconds for ball 1 to 3 meters come down, right? So now I need to find out H2. The same for H2. Formula is the same, half of g t squared, right? But we have to be careful for the time because its time is half a second less because it starts 0.5 second later, right? So from here, I will find out H2, which is 0.39 meter. So if I have H1 and H2, then simply H is H1 minus H2, which is 2.61 meter. Okay. Again, I let you guys to take your note. And if you have a question, please ask while I'm quickly checking the chat things. Okay. All right, so let's move on. Apparently you guys are smart and good and get to the more exciting topic, which is a curvilinear motion. So this time, instead of a straight line, things can move on any graph, on any path. But still we have a particle. So maybe not that much exciting when it is particle. You guys maybe wish to get soon to the rigid bodies when the sizes matters. But for now, we have to be patient. Okay, so we have a particle. And let's draw the things A and acceleration and velocity for this particle. So keep in mind, velocity is always tangent to the path, right? So this is our velocity, V. Of course, it's a function of time, but I don't write T. So this is V. So next time when this particle is moving, let's say the particle's coming down somewhere down here maybe, then we'll see this vector is changing its direction. And maybe if it has acceleration, it also change its value. So unlike the previous topic, which was a linear, rectilinear motion, a straight line, now velocity change its position. So, but we need to keep in mind that velocity is always tangent to the path. All right. What about acceleration? So acceleration, unlike the rectilinear motion, now can have two components, normal and tangential component. So let's say the particle at a certain point, maybe this point, it's going to have one tangential component, like tangent to the path, and it's going to have one normal component, which is perpendicular to the tangential component. So if I can, okay. So we call this one AT, tangential, and we call this one AN, normal. And if we keep in mind, if we find the resultant acceleration, like if we combine these two, the result is not tangent to the path, right? So it can be any vectors. So this is A, total A, okay? So to solve these sort of problems, so let me then also write these things. So then you remember acceleration has both tangent and normal components. All right, the tangential, of course, is tangent, and the normal is normal to this curve. And when we say normal to a curve, it means if you draw a tangential line, right? If let's say if I draw a tangential line somewhere, let's say at this point, if I draw a tangential line, so then by normal, it means like a perpendicular line to that tangential. So this is the normal direction, and this is the tangent direction. Okay, so to solve these problems, we basically use two systems or two coordinates. Depends on the problem. One is the X and Y coordinates. And another one is N and T or T and N coordinates. Okay, it depends on the problem. One of these two. Let's see what is XY. So we call it XY system. Let's say we have a path, right? This is a path that things are moving, and we have the particle somewhere on this path. Oops, doesn't work. Okay. So, and this particle is moving, so we know this is its velocity, v. So what I need to do is at a reference, depends on the problem, it can be anywhere. I can select an origin and say, well, this is my X axis and this is my Y axis. So this is X and this is Y. So then simply I will say, if I connect the origin to that particle, we call this R. This is the position R, which is a vector, right? And what we will write then is simply we say R is equal to, which is a vector, is xi plus yj. Again, you learn from math, I and j are simply the unit vectors. So this is I and this is j. When we write I and j, this is just for simplicity to tell how many units in x direction and how many units in y direction. So I just, let's say this is I and this is j, all right? When I write R is 10I plus 5j, and then everybody knows that I'm talking about 5 units for x and 10 units for y. And what about velocity? Velocity is a vector which v, similar to what we learned, is just a derivative of position. It is x dot I plus y dot j. And simply for acceleration, acceleration is x double dot I plus y double dot j. So in other words, we treat a 2D curvilinear motion more like a linear motion, but we break it down to x and y, to its x and y components, right? This is what we do. In other words, let's say for like this velocity, this particle that I have, I break down it to its component. I simply, let me get rid of that. Maybe I write it down somewhere here. Okay. Okay. Now, if I find the component for this velocity, right, the components is Vx and Vy. Which this Vx, in fact, is what we call now here x dot, right? So if I want to write it down the way that maybe you like, it can be Vxi plus Vyj. And the same for acceleration. It is Axi plus Ayj. All right? Similarly, these components, like this particle has acceleration components. Maybe this is Ax, and maybe this is Ay. Maybe it is bigger or smaller, we don't know. So this is Ax, and this is Ay. But always keep in mind, as you can see from this picture, this Vx and Vy, the result, this pink V is tangential, is tangent to the path. But Ax and Ay, if I find their resultant, they may not be tangent to the path. All right? Is it clear, guys, so far, what we are doing? Are we good? And again, don't be intimidated by these shape and things. When we solve problems, you will see how easily we just use these. This is just the formality to know where things comes from and the basic formula. Is there any questions so far, guys? Are we good? Good. Okay. So to summarize, when we have a curvilinear motion, we treat it in an XY system like two rectilinear motion, two simple rectilinear motion, one in X direction and one in Y direction. As if that you have a camera, let's say you have a camera, one is moving along X, it doesn't see, so this is your eyes or this is your camera, if I can draw it, right? It doesn't see anything in Y direction. It just see one particle moving along X. It just see one horizontal line. What is its speed? It's Vx. What is its acceleration? It's Ax. And then we have another guy standing here. He doesn't see anything in X. He just see one particle moving up and down with the speed Vy and acceleration Ay. Okay? So let's stop here. And on Friday, we'll continue with solving this example. I'm going to post basically these notes on Canvas, but on Friday, we are going to solve example 3, 4, and 5. So if you have time, take a look at this example.